Hey guys, this is Mo. This is about 9.3. Most of 9.3 you kind of actually know how to do with limits from the left and the right, but there are a couple things we don't know how to do. So the first thing is making a picture from information they give you. So like if we look at these tricks that I put in the Miss Mo's notes, or I think it's called Math 1325 student links, and then go down to handouts, and there should be something that says 9.3, and that's the thing I'm looking at. So anyway, this says that f of x equals y is a point with a closed hole on your graph. So this example says f of 2 equals 6, and you'll be given something like this on your homework. Like, for example, here's your homework, and it says f of 3 equals 1, and then a little semicolon, something else. So this f of 2 equals 6 is a closed hole. So this 2 in the parentheses after the f is the x value, and then the number that we're equal to is the y value. So at 2 to the right, 6 up, there's a big fat closed hole. Yeah, so on your homework, if it gives you f of something, there has to be a closed hole there. Okay, then they're going to give you something about a limit, and limits are sort of like x's and y's. Kind of, sort of. They're more detailed than that. But so if they give you a limit, the number that the x approaches is the x value, and then whatever you're equal to is the y value of a point. So say I have the limit as x approaches 2, f of x equals 3. Well, the 2 is the x value, and the 3 is the y value. So we have a point at 2, 3. And because that is the limit, that means that the limit from x approaches 2 from the left is 3, and the limit as x approaches 2 from the right is 3. And we know that both of those are 3 because in the previous sections we learned that if you want to take the limit as x approaches just a number, you have to look at the left and the right, and if they're the same, then that's the limit as x approaches just that number. So because we have the limit as x approaches 2 is 3, that means we're going to have a point at 2, 3. So we go 2 right, up 3, and we should have a point. And it doesn't matter right now if it's open or closed. I'll tell you something in a minute. Okay, and then if you look at this dot that is drawn, the curve from the left leading up to it ends at that y value of 3. And the curve on the right leading up to it ends at that y value of 3. So when you have a limit, your curve is gonna meet at that same point, because as x approaches 2 from the left and right, it's 3. Okay, let's see here. The next thing is, if you see the same x inside this f of x up here, which for us is a 2, and x approaches a number, so for us, x approaches a 2, so since these are the same numbers, 2 and 2, check to see if the y's are matching. If they are not matching, so let's look at my y's. My y's are 6 and 3. Well, that means they're not matching. That means that the point you drew for that step that we just did should be an open hole. So step 1, the f business, tells us where there's a closed hole, a dot. Step 2, the limit business, tells us that our curve is going to meet at the same y value. Okay, but then if those two suckers are different, if they're equal to a different number, that means that this closed dot is not on the curve with the limit. So this closed dot, since it has a different y value, it's just hanging out above or maybe below, but it's not on the curve because the y values don't match. So on your homework, if the y values don't match, draw an open hole on that second step. Okay? If they have oh, okay, and then that's it pretty much. Okay, and then it's continuous if there's no hole at the x value that they're asking about and the limit exists, meaning it's the same from the left and the right. So, for example, here at x equals 2, we're not continuous, and the reason we're not continuous is because we have a hole right here on the curve. And the reason we know we have a hole on the curve is because the limit y value and the function y value were different. One was a 3, one was a 6. So I know I have a hole on my curve. So it's not continuous at x equals 2. But say it asked, is it continuous at x equals 0. So let's see if it's continuous at x equals 0. That means we look for when x is 0 right here. We go up to the curve. Oh, here's a curve. And it's only continuous if there's no hole. Well, poop, I got a hole. So not continuous at x equals 0. Or x equals 2 because there was another hole. So continuous basically means you can trace the curve and never pick up your pen. So if I look at this curve, if I try and trace it, I have to pick up my pen wherever the hole is. So it's not continuous. Okay, let's look at how to tell from equations. So for equations, we could either throw it in our calculator and look at the picture, or we can do some algebra. Let's learn how to do the algebra first. So for fractions, let's say we have y equals 2x plus 1 over parentheses x minus 3, x minus 4. Okay, so I already gave you the factored version. You're welcome. That's how the homework does it. I'll give you one that's not. Don't worry. Okay, so first, we want to know what makes this problem bad. Well, in 9.2, we learned that the things in the bottom create vertical asymptotes, and that creates a break in the graph. And when you draw an asymptote, you have to pick up your pencil to draw it. So that's where the picture is not continuous. So to figure out where those asymptotes are, we're going to take these denominators. So we're going to take out the bottom, and we're going to factor it. So we're going to take out this x minus 3, and we're going to factor it, but it's already factored it because it just has x. If maybe it was a squared, it would not be. So we take the bottom, it's already factored, now we equal it to 0. So let's put some equal zeros on these things and solve for x. You add 3, and you get x equals 3, and then you add 4, and you get x equals 4. So if I were to look at the picture of this, that means that my graph will jump at 3 and 4. Maybe there's an asymptote, I'm not sure. Okay, so I'm gonna press graph, and my graph is zoomed out. Let me zoom standard, so press the zoom, the gray button, and then number 6. And I should, okay, well, I definitely have something at x equals 3. 1, 2, 3. And then at x equals 4, you can't see it. There's not a break in the graph. But if I go to my table, at x equals 3 and 4, there's an error because one of those is probably an asymptote, one of them is a hole. So you can do it mathy or calculator. Either way, everything is good except for that 3 and 4. So if we go to our table, every single x value has a matching y value except for 3 and 4. So that means we need to say that all the x's are great, except for at 3 and 4. So it says, I think the exact directions in your homework are determine where the function is continuous. So it's everywhere except for here. So starting all the way in the negatives, all the way up to this 3. And then from 3 to 4, there's some points in there. So 3 to 4. And then from 4 all the way to infinity. And I'm going to use parentheses. And I think your homework wants to use like a U, not the keyboard U. It's a button on your homework toolbar. So do not use the keyboard U. So this means that every single X value in this calculator has a matching Y value, except for at 3 and except for at 4. And if I were to look for an X value of like 3.1, I would have a matching Y value. So anything in between 3 and 4 also exists. We just can't see it because these are whole numbers. Okay, let's try one where we have Y equals 2x plus 1 over x squared plus 9. Okay, so if I try and factor this denominator, I do x squared plus 9. But then some of you are thinking, oh, this is x minus 3, x plus 3 when I factor it. No, it's not, because there's not a minus sign on that 9. Ah, poop. Okay, so since I can't factor it, maybe I can solve it. Like put equals 0, so x squared plus 9 equals 0. And then use something called the square root property, where we just move everything away from the tiny 2. Using opposites. So subtract 9, and we get x squared equals negative 9. Then to get rid of a tiny 2 in the air, we put a house on it. But when you take the square root of a negative number, it gives you imaginary stuff. And when it comes to continuous, we don't care about the imaginary world. We just care about the real world. So since this gave me x equals a bunch of imaginary numbers like 3i and negative 3i, and that's not included in the real world, then we're just going to say every x value is good to go, because we could not solve for x and get a real number. So this sucker is going to be continuous everywhere from negative infinity to positive infinity. That means if we put this sucker in the calculator, it should be one smooth, solid curve, and there will be no picking up your pen from the paper. Okay, let's look at this next one, radicals. Radicals is pretty simple also. You take the inside of the house and make it bigger than or equal to 0. So let's say you have f of x this time instead of y. F of x equals 2x minus 9 in a square root. So first what you do is you take that 2x minus 9 out, write down greater than or equal to 0, and get x by itself. So add the 9 over, 2x bigger than or equal to 9. Divide the 2, divide the 2. And this says that every x bigger than or equal to 9 over 2 is good to go. Everything not that is bad. And 9 over 2 is another way of saying 4.5. So if I wanted to look at the picture of this, I could type it in to my y equals and go to my graph, and it looks like the graph only exists around 4.5 and after, so nothing happens before. So we're going to say it's continuous from 4.5 all the way to the end of the curve, infinity. And I'm going to put a bracket around this 4.5 because of this equal to underneath the gator. So that's why I have a bracket. Okay, anything else that's in your homework, it will be continuous over negative infinity to positive infinity, unless they give you a picture. So in your homework for the equations, you should have a fraction problem that gives you an answer, a fraction problem that just is useless and you get negative to positive infinity. Then you should have a square root, and then every other type of equation should be continuous over negative infinity to positive infinity. Okay, let's look at the back of this sucker and see what greater than, equal, and less than equal means when you're looking at a picture. Okay, so if you have f of x greater than or equal to 0, that's where the curve has positive y values or is above the x-axis. So our x-axis goes side to side. So if we look at this picture, let's find the pieces that are above the x-axis from here. So this has a positive y value. This hump in between have positive y values. This open hole with this tiny little hump over here. And then halfway in between this curve and all the way up. So these are when f of x is bigger than or equal to 0. So now we're going to say where it happens. So we're going to go from left to right, and we're just going to use the x values. So for this sucker right here, let's pretend these are arrows. Yeah, okay. Okay, now that we have arrows, I can do it. Okay, so we're going to describe this segment of the curve from left to right using your x's. So from left, it looks like there's an arrow, so that's negative infinity. And then it stops, I don't know, right here at negative 6.8. I think your homework will be easier because there will not be decimals. Okay, and infinities use parentheses. So I'm going to put a parentheses. And then solid dots or curves use brackets. So when I stopped right here at this negative 6.8, that was a solid curve. So I'm going to use a bracket. Then I'm going to use a U because there was more than one piece that was above the x-axis. Okay, now let's look at this little part right here. From left to right is -4 to -2. And on the left, there's an open hole. And open holes and asymptotes use parentheses. So right here at -4, we're going to have a parentheses. Right here at -2, it's not a solid dot, but it is a solid curve, so we use a bracket. And then U, there's another one. This little mountain over here, it starts at x is 0, ends at x is 2, so 0 to 2. And both at 0 and 2, it's a solid curve, so I'm going to put brackets. Then let me put another U. And this very last piece, it starts at maybe 4.5 and goes all the way to the right. So that's infinity. But that 4.5 is on a solid curve, so I use a bracket. And then that arrow uses parentheses. Okay, now to do the opposite, we just do the opposite. So f of x less than or equal to 0 looks at the stuff below the x-axis. So let's describe the f of x less than or equal to 0 for below the x-axis from left to right. So right here it's like -7 to what's the x value right here? Not -2, -4. So from -7